Hey, welcome to the second lecture in this series on atomistic simulations to model materials, properties, and structure. So yesterday we saw various applications and different kinds of different levels of theory at the atomistic length scale, starting from density functional theory to ab initio molecular dynamics and molecular dynamics to solve various problems in the domain of materials and interfaces. The theory backbone behind using molecular dynamic simulations is the discipline of statistical mechanics. So all the correlation that we develop to calculate properties of materials are based on principles of statistical mechanics. So it makes sense to introduce you all a little bit to statistical mechanics. This, by the way, is a class that I teach typically for a full semester. So there is a lot to be unpacked in statistical mechanics. What I will do in today's lecture is give you a broad overview of the basic theory. Okay? So how many of you have some background or have heard of statistical mechanics or statistical thermodynamics? Just wanted to get a general sense. Okay, some of you have. Okay, great. So so I'll assume that there is a little bit of a background. So statistical mechanics is the concept of looking at microstates of a system or material. So if you have a material and you are interested in quantifying or measuring its properties, such as mechanical property or thermal properties, such as thermal conductivity or diffusion through the grain boundaries in that material, you can characterize and measure at the microscale or continuum scale some of those properties. Or obviously, like we discussed, you can run calculations to determine those properties based on atomistic simulations. So the basis of that is what is the microstate of a system corresponding to a macro scale property material in equilibrium. What I mean by that is, at the end of the day, in atomistic simulations, what we are dealing with is a collection of atoms or molecules, right, or units if it's a polymer. So what are the energy states available for these, let's just say, particles for the sake of generality? What are the microstates available for these particles to fill, and what are some of the favorable distributions of these particles at various quantum states, and how does that impact the physical behavior or properties of that system? That is through the concepts of statistical mechanics. There are varied applications of this beyond just being able to calculate properties. For example, when you get at very high temperature applications or very low temperatures, such as cryogenics, materials display some very unique behavior and properties, for example, superconductivity. And a good understanding of the microscopic states of the system and how it's constituted helps us understand those phenomena and physics. So this field has developed tremendously since, I would say, the early part of the 20th century, since the 1910s and 1920s, in conjunction with quantum mechanics. So they go hand in hand. Quantum mechanics, and I will introduce a little bit of quantum mechanics in a couple of lectures, has to do with the behavior at the smallest length scales, while macroscopic behavior, there has to be a bridge in the length scale and time scale between the very fundamental electronic and protonic states to the continuum scale. You could think of statistical mechanics to be that bridge. It provides statistical principles to infer from quantum level behavior of materials to their macroscopic properties at equilibrium. So fundamentally, what these materials that we simulate with any atomistic simulation tools, what we are doing is basically solving Newton's law of motion for each and individual constituent atom or molecule that material is made of, right. So obviously we are all familiar with Newton's law of motion. It's just F equals ma, let's say. So the challenge here, though, is if you take just about an inch cube of simple ideal gas, let's say air, we are talking about 10 raised to 20 number of particles in there, right. And if you write an F equals ma equation for that many particles, you basically have a huge degrees of freedom to describe the state of the system. So, that is where the statistics come in handy to describe the state of those systems, even small systems. Fundamentally, if you have a molecule or an atom, it has certain degrees of freedom. Okay? So, if that atom is in electronic ground state, a molecule with a number of atoms, as it says here, has 3 times a degrees of freedom. It is not very difficult to understand if you just think of a argon atom. What it does, it just has the kinetic energy, it is moving around, right, with velocities in the x, y and z directions basically, which are its 3 translational degrees of freedom. But as soon as you go into more complex structures such as diatomic species like oxygen or polyatomic species such as water or whatnot, it becomes a lot more complex and there are new degrees of freedom introduced to that structure. By degrees of freedom, what we mean is what are different ways in which you can store energy, what are the different forms of energy in that molecule or atom that we are discussing, right. So, the general idea is if you have a molecule such as let us say oxygen, right, it has 3 degrees of translational freedom. If you take the center of mass of that oxygen molecule, it can have 3 translational degrees of freedom. But if you use this expression, you can see that oxygen has 3 times 2, that is, it has 2 atoms of course. So, 6 degrees of freedom. So, what are the other 3 degrees of freedom? Any thoughts? 3 are translational. There is rotation and vibration. So, for this linear simple molecule, there is only one vibrational mode along the bond that connects this, and then there are 2 rotational modes or rotational degrees of freedom. One rotational degree of freedom is about that axis, and then the other direction there are 2 axes. So, those are the 2 degrees of freedom. So, 3 translational, 2 rotational and 1 vibrational degree of freedom. It gets more complicated as we go from let us say a molecule like oxygen to something like as simple as even water. So, the total number of degrees of freedom in water are obviously 3 times 3, which is 9, out of which again 3 are translational degrees of freedom based on the motion of the center of mass of water molecule. And then how many rotational and vibrational degrees of freedom do we have? That becomes the question, right. So, if the molecule is linear or not, that determines the number of rotational degrees of freedom. So, as it says here, if a molecule is linear, it has 2 rotational degrees of freedom just like oxygen molecule, and if it is non-linear, then it has 3 degrees of freedom. Okay. So, how many remain then? 6 minus 3 translational and 3 rotational in case of water. So, there are 3 more remaining. Those have to be vibrational modes, which are captured in this diagram. It shows you the 3 different vibrational modes for this nonlinear water molecule. And spectroscopic measurements are able to look at the principal frequencies of vibration, amplitudes of vibration, etc., and compare them with statistical mechanical analysis as well. So, why are degrees of freedom again important? Because those are the different ways in which internal energies in the molecule, in this case water, manifests itself. So, we have to understand what those are. But by the way, I have to say that if we go to polymers, it gets more complicated. So, I am not discussing polymeric structures. They might have more rotational degrees of freedom just because of their conformation or configuration.
So, that you mean by chirality also?
By what?
Chirality.
Chirality, yes, there is chirality. So, polymeric structures are more complicated in terms of their distribution degree. Yes.
So, which type of vibration is happening? Is it symmetric or?
In this water molecule, there are these 3 different, there is stretch, there is this twist and bend. As you can see, this one is just stretching of the bonds or angles, this one there is a bending, and this one is a twist. So, 3 different degrees of freedom.
So, when you are talking about the spectroscopy,
Mm-hmm.
you mean like Raman spectroscopy,
Right.
and also
Mm-hmm.
these type of.
So, spectroscopic measurements can get into the vibrational modes, right. Okay, so now that we know the different degrees of freedom, what is the principal problem that we try to solve in statistical mechanics? The problem is simple. It's you have n particles, those particles can be electrons, protons, photons, atoms, whatnot, and you want to distribute them in various energy levels. These energy levels are designated as epsilon, and J is just a subscript. J is a number, so there can be 1 million energy levels. So, in that case J is 1 to 1 million or 100 different energy levels, and then there is a degeneracy Gj. So, the question, and I will explain to you what these degeneracies and energy levels are in a moment. So, the fundamental question is, what are the rules that determine how these particles, electron, photon, proton, whatever, or any atom that you are distributing in various energy levels, what are the rules for distributing them? Depends on the nature of particles. Okay. And what you can do is you can do a combinatorial analysis, right, permutation combination rules or expressions to determine how many different ways you can distribute a certain number of particles, uppercase n, in these energy levels, and each energy level has a certain degeneracy. So, this is an example of what I mean. So, this plot, this is not really a plot, it is a schematic. It shows, you can see some boxes, right. What are these boxes? These boxes are what we can call quantum states. These are distinct quantum states, and on the y axis we have energies. So, you have, as you can see, 1, 2, 3, 4 horizontal lines, each of which has a certain value of energy, arbitrarily named here as 0, 1, 2, 3, does not have to be that, this is just an arbitrary name. So, we have a certain number of quantum states per fixed value of energy. So, there are 3 different quantum states at an energy level of 0, 3 at energy level 1, and 4 each in this example at energy levels 2 and 3. So, there are 4 energy levels and there are 14 different quantum states. So, the number of quantum states that are at each energy level are approximately the same amount of energy. Their energies can vary slightly, but compared to the difference in energy between 2 different energy levels, the difference in energy between these 2 quantum states is negligible. So, we can just approximate them as approximately the same energy, each of these quantum states. So, we call this degeneracy, which is the number of quantum states at a certain energy level, and we designate that as Gj. So, in this case G0 in this example is 3, G1 is 3, G2 is 4, and so on and so forth. So, that is what I meant in the previous slide. Oops, let me erase this. So, the fundamental postulate is that each quantum state is about equally likely to be filled. Okay. Even though their energies are slightly different, they are about the same, and like I mentioned, the number of quantum states in each energy level is called a degeneracy. Questions? Okay. So, coming back to that previous slide where I introduced the main idea of how we distribute these particles in different energy states. There are 3 different very popular distributions depending on the nature of the particle. The most common, or the simplest one I would say, is what is called Boltzmann distribution, and the name of the statistics associated with it is Boltzmann statistics. So, this is Boltzmann distribution. So, what this expression tells us is how many different ways can you distribute n particles in a system with Boltzmann like behavior, like Boltzmann particles that follow Boltzmann statistics, where you have nj number of energy levels and each of them have a degeneracy of Gj. Okay. So, this is the number of ways you can distribute it, and this quantity W is called thermodynamic probability. So, it is basically counting how many ways you can distribute these particles. What is the key idea behind Boltzmann statistics, or what type of particles would follow this kind of distribution? Number one, the particles have to be distinguishable. So, let us say you can number or name each particle, which is difficult to understand because in real life if you have the same atoms or if you have electrons, they are indistinguishable. Most quantum mechanical particles that we deal with are indistinguishable, but in this case Boltzmann distribution deals with distinguishable particles. And the second postulate is there is no limit on how many particles you can put in each quantum state. So, going back to the previous slide, each of these boxes, if it's Boltzmann distribution, you can put as many particles as you want. There is no limit. Okay? So, those are the rules, and particles that obey those rules are called are said to follow Boltzmann statistics. Okay? Okay, sorry. Trying to erase. Okay, now it works. The next distribution that I will introduce you to is called Fermi-Dirac distribution or Fermi-Dirac statistics. So, this is a separate set of rule. This follows for particles that are indistinguishable. So, electrons, for example, follow Fermi-Dirac statistics in their distribution, and there is a rule that there is a maximum of one particle per quantum state. This is actually also in chemistry or physics known as Pauli's exclusion principle, and we will get into the symmetry and antisymmetry aspect of wave functions. It involves quantum mechanics. I haven't introduced it, so I do not want to get into it as yet, but basically electrons are an example, or nuclei of odd mass number is another example of particles that follow Fermi-Dirac statistics. Boltzmann's the third one is Bose-Einstein statistics. So, what is the characteristics of particles that follow Bose-Einstein distribution? These are again indistinguishable particles, just like Fermi-Dirac, and in this case though the difference is there is no limit to occupy each quantum state. So, that is the principal difference between Fermi-Dirac and Bose-Einstein statistics. Yeah.
Sir, among these three, which one is dependent on temperature and which one is not?
All three will have temperature dependence on how you want to distribute those particles.
So that means at 0 Kelvin, the electron also will be affected?
Yes. So, just think about it. You are asking this in advance, but I will address it. So, let us think it is 0 Kelvin. What happens at 0 Kelvin? All particles try to flock to the lowest energy state, right. So, if you have a Bose-Einstein system, bosons, then they will try to fill not only the lowest energy level, which is 0, but even if you have 1,000,000 particles, bosons, they will all fill the lowest energy level. So, basically the entropy of the system will be very low in case of bosons, while in case of fermions, which follow Fermi-Dirac statistics, they will first fill out the lowest energy state and then it is full, then they will go to the next energy state level, next energy level, and they will stack up. So, band structure in semiconductors or metals, like if you get into that distribution of electrons, you are looking at Fermi-Dirac statistics, and there is a Fermi level associated with the energy to which it is occupied. But in case of bosons, what we have is Bose-Einstein condensates, because they kind of flock and condense to this lowest energy level that is possible. Okay.
Boltzmann distribution, is there any certain example which follow?
Great question. Unfortunately, this simplistic Boltzmann distribution is not physically very meaningful, but we will see that if you are looking at systems that have a reasonable density, then the Bose-Einstein distribution, Boltzmann distribution, and Fermi-Dirac distribution all will converge to a form which is called modified Boltzmann distribution. So, this n factorial, I did not get to the math of it too much. This n factorial is accounts for the distinguishability or not of those particles. So, one can prove and show that as we get to a certain set of densities, the quantity Gj over Nj becomes very large, or rather Nj over Gj, the number of quantum states that are available compared to the number of particles is large. And when that happens, then all of these distributions kind of converge to, I can write this expression here, to modified Boltzmann expression or distribution, which is basically omega thermodynamic probability is this, okay? And this one will be physically meaningful. For example, if you are dealing with ideal gases, let us say helium, and want to understand its properties and behavior, when these are ideal gases, which is high temperature or low pressure, these will follow typically modified Boltzmann distribution. Okay. Other questions? Okay, let us move forward. So, these are the three distributions. Now, we have 3 distributions, doesn't mean these distributions are all equally probable, right? These are just telling you the number of ways in which you can distribute particles in quantum states. But there are constraints in real system. What are those constraints? Maybe the volume is fixed, the number of particles could be fixed, and that system could have a fixed internal energy U. The most common restriction that we apply to find out an equilibrium distribution of n particles across these energy levels with degeneracies is that the total internal energy U is a fixed quantity. Okay? So, as soon as you do that, let us say you have 1 billion different distributions that are possible, most of them are not valid, because you have introduced a new constraint that the internal energy of this system has to be fixed. So, to determine the most probable or equilibrium distributions, what we do is called a constraint minimization. Okay? With the principle of Lagrange multipliers in mathematics, you can do a constraint minimization of a function. Basically, you maximize the thermodynamic probability for a fixed number of particles that you are trying to distribute with a fixed constant internal energy, and the total internal energy is given as you take each energy level and multiply that by the number of particles that are in that level, and you add up. So, it is a summation of n j epsilon j that gives you the total internal energy. So, this is the constraint, and you are trying to maximize the thermodynamic probability function omega. What was that function? In the previous slide, I showed you that function. For depending on the type of distribution, you have different functions for omega. So, you want to maximize omega while keeping the number of particles and u the same. Now, if you follow those steps, I am not going to derive it. If you are interested, please refer to any statistical mechanics book, such as Sontag's book that I have referenced for that. It is pretty straightforward. So, you either get this modified Boltzmann distribution if you are dealing with that, and this is a very popular distribution to get into the details of properties of ideal gases, like I said. So, if you just plot this distribution, energy level as a function of the number of particles over the degeneracy, you get this exponentially decaying function. Okay. For Fermi-Dirac statistics, you get a slightly different distribution, and for Bose-Einstein statistics, you get a different distribution. So, the first thing you might be thinking, well, we already know what epsilon j is, energy level, we already know what degeneracy is, g j, but what is alpha and beta? I haven't introduced alpha and beta, right. So, alpha and beta are undetermined multipliers. So, when you do a Lagrange minimization of a mathematical function, then each constraint you have in that system, in this case there are 2 constraints, the number of particles are fixed and total energy is fixed. Each constraint leads to one undetermined multiplier, and alpha and beta are those 2 multipliers. Okay. So, we want to know what those multipliers are, right. So, if you just sum up, let us say you take the modified Boltzmann distribution and sum this up, right, what you should get is the total number of particles if you sum n j. And when you write it mathematically, you can get an expression for the first undetermined multiplier, which is alpha, not in a straightforward manner, but it just says exponential of negative alpha is given by this quantity, the total number of particles over a certain summation. Okay. It is a much more complicated derivation to find beta. One way to determine beta is take a system of monatomic gas with 3 degrees of freedom and write its translational energy and then sum it up. If you do that, you can show beta is simply given by 1 over Boltzmann constant times temperature. Again, I am not doing that derivation here for the sake of time. Questions?
So this nj is basically the number of particles in that particular
Energy level. Exactly. So, I showed you those energy levels in a simple manner, these boxes, as an example, of course. In real life, there will be many more energy levels and degeneracy, but it's the, it's the distribution. How are particles distributed in the system amongst various energy levels? Because guess what? If we know that, if you have an answer to that, we are able to, as I'll show you soon, we are able to calculate most thermodynamic properties: internal energy, Helmholtz free energy, enthalpy, specific heat, entropy, okay, of that system.
Entropy is simply ln of this W which
Yeah, I'll get to that just in a couple of slides. You're right.
how to determine this beta on once again you told.
Sure. the way to determine beta is you can do it a few different ways. The simplest way is to take a monatomic ideal gas, let us say argon, and look at its 3 different degrees of freedom, right, which is the translational degree of freedom. What are the energies? So, what are the different ways an argon atom can have energy? The translational energy, anything else? Of course, it can have electronic energy, right? It can have nuclear energy as well. The nucleus has a ground state as well. But it so happens the electronic and nuclear ground state to the next excited state is kind of a huge jump. So, we just work with just the ground states and ignore that energy. So, then the only mode of energy is translational. So, you can write an expression for the kinetic energy directly of that argon atom. Okay. Across a small difference in energy levels d or velocities dvx, dvy, dvz, and then you have to basically add up all these energies by integration, and that should give you the total internal energy. And if you follow that derivation and you apply kinetic theory of gases, then you can show that beta is 1 over kBT. Okay. That is how you can derive. So, the key thing though is just to make sure I get this across, I started out with the total number of distributions, and for a realistic system that is at a certain state, equilibrium state with a certain internal energy U, I showed you there are only a few distributions that are physically meaningful. Every other distribution is not physically meaningful, right. So, these distributions that I have just derived are called most probable distributions in each of these ensembles or each of these systems, be it the Bose-Einstein, the Fermi-Dirac or the Boltzmann. Okay. The key idea is a macroscopic or equilibrium state of a system. Let us say you have a block of iron and you are interested in knowing what its specific heat is at a certain temperature, right. That macroscopic equilibrium state in principle is resulting from this microscopic distribution of the particles or atoms of iron that are filling up the different energy levels that are available to it, governed by quantum mechanics, right. But the idea is in continuum mechanics or at a macro scale, we do not see any fluctuations. We have that block of iron, its volume is not fluctuating, it is just stable at that equilibrium state. But at the microscopic level, there are some fluctuations. Even though this is the most probable distribution, there are a couple of other feasible distributions around the most probable distribution. So, let us say I kind of draw the number of distributions here somehow, just to visualize. So, there is the most probable distribution with the highest probability, but there are other distributions right around it, and at equilibrium there is a slight fluctuation in these distributions at equilibrium of that system, and these fluctuations result in a lot of the properties of the system that we will look at. Okay. Okay. So, this is pretty complicated. How do we kind of summarize the quantum level behavior of this system? What is that one function, for example, that can summarize the degeneracies and energy levels that are available to a certain system under a certain constraint? For example, like I said, you have a block of iron at a fixed temperature and at a fixed volume. As soon as you determine that in quantum mechanics, automatically you can solve the Schrodinger's equation to come up with the different quantum states. Okay? And the function that describes this is this function, which is known as the partition function z. So, what is the partition function z? It simply mathematically is this summation. It is the summation of all the degeneracies multiplied by e raised to negative epsilon j over kt, because beta is 1 over kt, right. So, why is this so cool, the partition function? As soon as you have determined the boundary conditions of that system, right, you have a particle in a box or you have a block of crystal in material, you can already determine the different energy levels and basically the quantum states and degeneracies. The application of this is most continuum scale property of the system or properties of the system, such as the total internal energy, can be expressed in terms of the partition function. Let us look at some examples here. By the way, partition functions have an incredibly complicated expression if you want to express it in terms of known properties that we can measure. Okay? But one case, which is monatomic ideal gases, the expression is rather simple. So, I will see if I can show that. Okay. So, for monatomic ideal gases, you can derive again from the same theory that the only energy for a monatomic ideal gas, the only degree of freedom is its kinetic energy, the translational energy. You can derive the partition function as a function of the volume of that system V and the temperature of that system T. What is H? H is known as the Planck's constant, right? And m is the mass of that atom and k is the Boltzmann constant. So, all of these are constants except the volume and temperature. So, for a monatomic ideal gas, it is the simplest system that you can think of. The partition function is given by that expression. Okay. Questions? So, yeah. Great question. The physical significance of this partition function is, it is a descriptor, mathematical descriptor of the various quantum states that are available to a system under certain conditions. For example, for this monatomic ideal gas, that condition is the size of the box in which it is present and the temperature of that system. So, if you change the temperature or the volume, these quantum states will rearrange and change. So, I will go back to my schematic here. So, these quantum states are not fixed, it depends on some boundary conditions. In the example I just gave you, if you just change the volume or the temperature, this will change. And as soon as this changes, the distribution has to change, right?
So, it is basically a mathematical representation
Of the quantum states of a system.
quantum states.
Exactly.
Like constants.
Yeah, that is
So
true.
the quantum states is changed by the particular number at that very energy level or by the amount of energy difference in between the states.
Good question. It's both. So, when we do quantum mechanics, I will show you some limited examples. For example, if you have a diatomic molecule like oxygen that has rotational degree of freedom, you can solve the Schrodinger's equation for that rotational degree of freedom to see what the different quantum levels are. In the example I am showing you, all the energy levels are stacked up equidistant, it does not have to be that way. So, for example, for vibrational modes, at first the ground state energy and the next few energy modes are kind of spaced out, but as you go to higher and higher energy levels, they become very crowded, right. So, it depends on the degree of freedom. The simple answer is the specific difference in the energy level depends on the degree of freedom that you are looking at. Okay. It is all quantum mechanics, that aspect. Okay. So, we have distribution, we have talked about partition function. What is the application of that? So, this slide presents various thermodynamic properties. I am not sure if you are familiar with the nomenclature here, I have not written it, it is pretty standard. U is internal energy, S is entropy, this is Helmholtz free energy, Gibbs free energy, enthalpy, P is pressure, and this is specific heat. Okay. So, these are different properties of only an ideal gas. Okay. We are not talking about interaction yet. If you have a solid material, there will be interaction. If you have a real gas, there will be some interactions between molecules, which is known as configurational energy. We have not talked about configurational energy yet. Think of independent particles, they are not interacting with each other. So, if you have a collection of independent particles, then if you know the number of particles which is related to the mass, if you know that obviously there is Boltzmann constant, if you have a certain temperature, then you can find its internal energy simply by, if you know the partition function. Okay. Now, the question is, how do you get the partition function? You have to apply typically some sort of a numerical simulation. In very simplified cases, for example, I showed you the expression for a monatomic ideal gas, you can theoretically write an expression for partition function. For real systems, let us say you have a polymeric material, to get to the partition function you have to solve either at the quantum mechanical level or use atomistic simulations to estimate the partition function, typically quantum mechanics. So, if you run a DFT simulation, if you want to, you should be able to get the partition function from that. Again, these are the different properties. Questions about these properties? So, the bottom line is all thermodynamic properties that we are interested in, most thermodynamic properties that we are interested in are expressed here as a function of simple parameters such as temperature, volume, etc., and the partition function or its derivative. Some of these have a derivative of the partition function with temperature or let us say with volume in case of pressure with volume. Now, these are all for modified Boltzmann distribution, these expressions. But let us say you have an electron or you have a photon. By the way, photons follow Bose-Einstein statistics. So, if you are trying to model a box with photons for photovoltaic applications, or if you are interested in a metal, conducting metal, and you wanted to understand its band structure, a collection of electrons, you cannot use these expressions because they do not follow Boltzmann distribution. So, in that case, you will have to apply either Bose-Einstein or Fermi-Dirac statistics. So, you can follow the same set of rules to come up with an expression for these thermodynamic properties for fermions or bosons. The expressions will be more complex simply because the distributions, the mathematical expression for those distributions, equilibrium distributions for Fermi-Dirac as Bose-Einstein are a little different from the Boltzmann distribution. So, the expressions will be a little more complex, but you can follow the same steps to not only calculate entropy, but all these properties that are up here. Okay. So, so far these properties are for independent particles that are just by themselves, right, if you have one atom of something. But in real applications, we are mostly interested in a group of particles, right. Let us say a collection of 1,000,000 particles or 1,000 particles, could be atoms in a crystalline structure, could be a liquid, whatever it is. So, how do we write the expression for partition function for not just one particle, but a collection of particles? So, that is known as a system partition function designated by uppercase Z subscript n referring to a collection of n particles instead of. So, if you just have Z, simply Z, that just means Z1, meaning one particle. So, the different energy, basically what I am trying to say, the different energy contributions are coming from the internal degrees of freedom, the rotational energy, the vibrational energy, the electronic energy, the electron spin energy, or the electrons going around the nucleus, that energy that but if you have a collection of particles, then besides that there is a configurational energy, because now you are talking about a collection of particles that are interacting with each other, right, electrostatically as well as dispersion and short range repulsion forces. So, this will now include that configurational energy typically, unless it is an ideal gas. Obviously, in case of an ideal gas, there is no configurational energy. By definition, ideal gas particles do not interact with each other. So, I'm just showing you the end result. It is not a very difficult derivation. You start from the previous expression and you can write the expression for all these energetic properties in terms of not just the single particles, but in terms of system partition function Zn. Okay. Questions? The reason I am presenting this here is very soon we will have to, for real problems, account for that configurational energy. We can't be just dealing with single particles or ideal gases, right. So, I am just formulating some sort of a model to get to that. Okay. So, there are many fun things that you can do just with this, just this understanding of that in a system at equilibrium, the particles, whatever they are distributed across various energy levels, right, microscopic at the various quantum states, I should say. What can you do with that? Well, not only calculate these properties, but you can get a microscopic insight into thermodynamics. Like you can think about first law of thermodynamics from a microscopic perspective, you can explain second law of thermodynamics and even describe or write an expression for entropy. So, at the macro scale, entropy is defined this way, right. It is a reversible heat transfer over temperature, it leads to that entropy change. But at the microscopic level, which we are discussing about, entropy is expressed as Boltzmann constant times natural log of the total thermodynamic probability. And one of you asked me about this expression, so you have probably seen this expression, at least some of you. The question is, why this expression? How did we get here? Why is entropy written as k times natural log of a thermodynamic probability, which is counting the number of ways in which a distribution can happen? It's not obvious. The way this comes up is the definition of entropy, right? So, entropy has to be related to the total number of states available to a system at a certain equilibrium condition. We know entropy is a measure of disorder in a system, right? We even know from the third law of thermodynamics what the boundary condition for entropy is, that a perfect crystal at 0 Kelvin you can achieve the lowest minimum entropy, which if it's a pure single atom crystal, then it can go to 0, right? So, entropy has to be related to the number of states available to a system. It is also an extensive property. We know that we combine two boxes that have a certain kind of chemical, the entropy is additive, right. So, entropy is an extensive property, it has to be related to the total number of states available, and this expression kind of catches both, right. How? So, if you take natural log of combinatorially, you can write the total number of ways in which you can distribute particles, right, in two boxes, one with a number of particles, box A and box B is going to be multiplicative, right. It is just from combinatorial analysis, it is the product of the ways you can distribute the particles in box A multiplied by the number of ways you can do that in box B. But if you now take a natural log function of this, you suddenly get natural log the sum of it, right. So, that works out pretty well. And then you multiply it with the Boltzmann constant, because that then makes the units of entropy dimensionally the same on both sides, joules per Kelvin or kilojoules per Kelvin, whichever you are using. So, that is how we come up philosophically with this expression of entropy. In here it says omega total, which is the total number of ways you can distribute particles in a system. But remember, for an system at equilibrium, there are only some distributions that make sense, right. And so, we can say entropy equals k times natural log of, instead of the total number of ways you can distribute, the most probable distribution, because there is at equilibrium there will be primarily that most probable distribution, which we derived earlier. Okay. So, now speaking of collection of particles, right, we talked about we hardly ever deal with independently one or two particles. We talk about a collection of particles and their properties, could be a certain material such as that perovskite we discussed the other day. So, get to the properties of a collection of particles, we discussed something called an ensemble. Ensemble means a collection basically. So, there are different kinds of ensembles depending on what thermodynamic or physical property you are holding constant. The key properties that we will talk about here is number of atoms in that ensemble N, the externally applied the pressure it is under P, the volume V, the temperature T. Okay. So, this is just definition. And we discussed this a little bit towards the end of the lecture on yesterday. So, one of the most common ensembles is the microcanonical ensemble, where the properties that are held constant in that are the number of particles N, the volume V, and the energy E. Okay. There is canonical ensemble, where the properties that are held fixed for this one is N, V, and T. There is isothermal isobaric ensemble, NPT, and finally, there is a grand canonical ensemble. Have you heard of grand canonical ensemble? Anyone here? So, and it is defined here. So, what are the three properties here? What is mu? The chemical potential, right. So, in grand canonical ensemble, each box in that ensemble can also exchange atoms. The number of atoms in this one is not fixed. All the other ones, the number of atoms are fixed. So, from a methodology perspective, if you are doing molecular dynamic simulations for your research, you typically do not work with grand canonical ensembles, but there are a few grand canonical Monte Carlo software that you can use if you have a surface absorption that you are trying to model, right, chromatography measurements or something. There is surface absorption. for whatever application. Okay. So, maybe a separations process, catalysis, then the grand canonical ensemble is pretty handy to work with those systems, because what you want to hold constant there is a fixed, let us say, partial pressure of a gas around a solid surface. So, the number of particles, if you have fixed and they start depositing on the surface, the partial pressure will change. So, you have to replace them by adding additional particle into that system, which is achieved through a grand canonical ensemble. Just this is kind of an aside. Okay, so what do these ensembles look like? What are we talking about? Okay. So, this is a this is a pictorial depiction in 2D of a collection of boxes. What you see here is like a grid, right? You can number some boxes 1, 2, 3, 4, 5, 6, etc., and go on, right? What are these boxes? Each of these boxes are the constituent of the ensemble, and depending on what kind of ensemble you are dealing with, the boxes look different. So, if you are dealing with a canonical ensemble NVT, then each of these boxes will have a fixed number of atoms n, a fixed volume V. By the way, they are also distinguishable, like I wrote here, you can number these boxes. So, I know exactly when you say you are talking about box 4, I know which box you are referring to. Okay. And then these boxes individually do not have to have the same have a constant energy U. So, the energy of these boxes can vary, but what has to be fixed is the total energy if you count all the boxes. So, the total energy in the collection of this system, I mean all the boxes included, has to be fixed. So, if there are eta number of boxes, right, then and if the internal energy average for each box is U bar, then as it shows here, the total energy of this ensemble is the number of boxes times the average internal energy. Okay. So, these are the boundary conditions. So, what do we want to do with this ensemble? As usual, if you are running an MD simulation, for example, you want to calculate the structure or some sort of a property of a collection of atoms. So, this is the foundation of that. So, here is some pointers. I already mentioned some of this. So, each of these particles in the system, so system meaning one of these boxes, like I said, have a fixed number of particles, fixed volume and temperature, but they have configurational energy. So, the particles in general can interact. Let us say we are talking about a crystal structure, silicon. Okay. So, then that silicon slab of silicon will have atoms that are interacting with each other. And so, there is configurational energy in addition to the kinetic energy and the internal modes. Okay. Like I mentioned, these systems are distinguishable and can exchange energy, but not mass, because the number of atoms are fixed. I already went over this. Each system is in some sort of a quantum state. So, what quantum state are we talking about? It is the system quantum state. Okay. So, you can come up with the quantum state of a collection of particles. We are not talking about now individual particle, but we are talking about the energy of the whole box, the system, which is basically a collection of atoms that are interacting. So, what are the modes of energy, internal energy for this interacting particles in that system? There is configurational energy, there is could be translational energy depending on the structure, rotational, vibrational, nuclear and electronic states, right. All of this could be there. So, together let us think about an overall system quantum state for this collection of n particles. So, we can follow the same rules, same methodology of constrained maximization of entropy, right, to come up with the distribution for this set of boundary condition. And if we can come up with that, then that is it. That is the rule we will follow for calculating the properties for this particular ensemble, which is a canonical ensemble. So, if you are wondering what is the average energy of this system, right, in a certain most probable distribution, we are not interested in any distribution at equilibrium states, we are only interested in the most probable distribution. It is given by the ensemble average of energy of each of these boxes in a certain quantum state. If in this community in molecular dynamics you hear about ensemble average quite a bit. So, this is what we mean by ensemble average. You have all these boxes 1, 2, 3, 4 through let us say 1000, each with these number of particles. If somehow you knew how many of these boxes are in a certain quantum state E I, so let us say you have some sort of a table here where you have eta I and EI, if you had that information by calculation, then you can do this averaging, which is known as the ensemble average, to get the average energy of this system. But it does not have to be just the energy. You could think of any thermodynamic property beyond just it could be the enthalpy, it could be the entropy, whatever property you are interested in can be obtained from this ensemble average. So, now I will throw out a question for you. So, some of you are doing molecular dynamics simulations and you are calculating ensemble average, but I am sure you are not modeling 50 boxes with the same system and calculating some sort of an average. You are just taking one collection of atoms, you are solving for its dynamics, and I will introduce that when I introduce molecular dynamics, but you are solving for its dynamics and then somehow you are averaging a certain property that you are interested in for that system. So, why do we call that ensemble average then? Any thoughts? What you are essentially doing is some sort of a time average, right? You're running, you're modeling a system over, let's say 10 nanoseconds, and you're getting many different configurations while you're doing that, and then you're finding an average based on each of those configurations over time. So, then what is the distinction between ensemble average and time average? Is it interchangeable? Are they the same thing, or are they a little different?
And there are total small n number of
boxes.
So, how they are interacting with the energy, how the energy is transferred from one to other, are they connected by bonds or?
Typically, no, they are not connected by bonds, and the answer to that question is they are connected to an energy bath, and that energy bath will compensate if that system is losing energy, so that its temperature will drop. If that happens, its kinetic energy of the particles in that system drops. That is directly related to the temperature of that system, because you are maintaining the temperature fixed. So, then that will be compensated by adding energy from that bath. On the other hand, if the temperature rises up because additional energy is available, then you drain some of that to maintain the temperature constant. But you are getting to the point about this particular box here. My question is, in these simulations, in for example molecular dynamics simulations, you are not typically looking at a collection of boxes. You are taking one box and you are modeling how the system changes over time, right? So, then why do we say that whatever we are calculating is an ensemble average? The answer is the ensemble average and the time average are not necessarily the same, but there is something called an ergodic hypothesis. So, if a system is ergodic, which is typically what we assume in molecular dynamics without actually proving it, but if we equilibrate the system well, typically ergodic hypothesis works out, means if you take one of these boxes and make it evolve over time in an equilibrium manner, holding the equilibrium constraints, then it is the same as you have basically a 1000 configurations, which is kind of the same as having 1000 of these boxes in the collection of boxes and getting the ensemble average. So, we make that assumption that they are basically the same, but it is not guaranteed. It is the ergodic hypothesis. Okay, sorry, written over some of the text here. So, now I just wrote an expression for average quantities, and without deriving these are the average quantities for a canonical ensemble. I am showing you the expressions for some of the common properties, thermodynamic properties, such as the average internal energy, the average entropy, Helmholtz free energy, pressure, and so for now, so those are expressions for those thermodynamic properties as a function of the system partition function, which we already discussed, right. So, if you have this collection of boxes with n particles, we can think of their partition function Zn. And if we know what the partition function is from these expressions, we are able to calculate these thermodynamic properties. So, herein lies the utility of ensemble average, okay, to infer on the properties of a system that is subjected to certain boundary condition. In case of canonical ensemble, it is NVT. For a microcanonical ensemble, it will be EVT. So, the boundary conditions will change, but you are able to now calculate properties depending on these boundary conditions. Questions?
Boundary condition is total length. From partition function, you get the average energy of the small cube, the small only one box.
No, you are taking the average of all the boxes. That's what this ensemble average is.
So how you link this average in sample to the partition function?
So the partition function is knowing the quantum state of the collection of all the particles in that box. Okay, so which includes, like I mentioned, any partition function is it's defined here already, right? So this partition function is given by this expression. So beta is 1 over kT. So the key idea is UI. What is the energy of a collection of n particles in that box? And you have to understand what those contributions are coming from. There is configurational energy because of interaction of the particles in that system, if it's not an ideal gas. So there will be dispersion, short range repulsion, electrostatic interactions. There's that. And then each particle will have an individual contribution. Let's say it's oxygen molecules, then they will have translational modes, rotational degrees of freedom, vibrational degrees of freedom, electronic states, electron spin, and nuclear states. So, so if you sum all of them up, what you get is a description of the quantum state of that collection of n atoms, which is captured through that partition function.
So in case of small n is not a particle, an ensemble of small n number of boxes. The small n could be time, could be any other thing.
So that's exactly what I was saying. So small n in this depiction is the number of boxes. It's like a supercell made of these tiny small boxes, right? And the theory is, if you have a collection of those boxes, right, under certain boundary conditions, exchanging energy with each other. What I said as an aside is, if you're applying molecular dynamics technique, you're not necessarily finding the ensemble average by looking at a collection of these boxes, but you're assuming you take one box and continuously evolve it through time while maintaining its total energy, for example, fixed, temperature fixed. Then it's basically the same as looking at individual configurations that are all in equilibrium, and the average you find from that time evolution is the same as the ensemble average that I've written here.
So in case of electrons, this also this is the way for that.
This is a general theory. The type of particle can be anything. The expressions, the type of particles can be it could be a collection of electrons in a conducting material. So you have a block of iron, you're trying to understand the band structure, then you can use the same principle to model that.
But sir, in that case, configurational energy of electron,
Right.
Repulsion between the electron clouds and as well as
Right.
interaction that we have to consider.
Yeah, you have to consider the interaction between the electrons if you're dealing with electrons. You could apply this model to a collection of photons, and basically you can come up with the radiation distribution, the black body radiation distribution, by modeling a collection of photons in a box. So this is very generic. Okay. So speaking of configurational energy, which is obviously relevant to most systems we look at. Like I mentioned, the system partition function depends on the internal energy, and one of the important components, we have already talked about the internal degrees of freedom already. So the additional one is the configurational energy. So what is the configurational energy? You have a particle of, just imagine you have a box with n particles, whatever that number is. At a certain moment of time, there is each of these particles are at a certain location within that box. Let's say the location is described by these vectors R1, R2, R3, Rn, right? Those are the locations of each of the particle. By virtue of their interaction, in principle, you have a configurational energy that will result from all the interaction happening between the particles in the system, not necessarily just binary interaction. it could be third order, fourth order, or they might interact in very complex manner depending on the structure of the system. Though we most often kind of assume just pairwise or binary interaction, but in real life the interaction will be a lot more complex. So this function is the configurational energy function, which actually depends on the position of all the atoms in the system or all the particles, let's say, in general, in that box. So if I want to find the partition function using the standard definition, the expression for that collection of n particles, then we can break it down, because this energy ui is the sum of the configurational energy and the energy contributed by individual particle in the system or individual molecule in that system, whatever it is, right. So exponential function wise, it becomes multiplicative, right. We have this, which is from the internal degrees of freedom, pretending as if all these particles are independent of each other, which is their internal degrees of freedom, and then there is a contribution from their interaction, mutual interaction. So this first term is essentially the same as one particle partition function Z1, which we have looked at in the past, right. That is how we started, single particle partition function. So that is what we have, and we have n times, so it is Z1 raised to n over n factorial. The reason we are doing n factorial is discounting that the particles are distinguishable. We are saying that they are indistinguishable. Okay. And then we have this other summation, which is much more complicated, the configurational energy. What do we do with it? So we can make some assumptions. If we neglect quantum effects, which means if we assume this is a continuous function, the configuration energy is a continuous function of the positions of the particles in the box, then we can convert this summation into an integral. Okay? And if somehow, let us just pretend, we had this function phi, this was given to us, then at least theoretically we can perform this integral to find the system partition function. So not an easy thing to solve, but at least we have a theoretical expression. Questions? So this is kind of a holy grail. If you are able to solve for this, then the rest of the theory is ready. You go back, you plug in the partition function, you calculate, you know everything about that system. The big deal is, what is the partition function, right?
Sir, in this case, for the discrete to continuous, we are neglecting
Oh.
the quantum effect.
It went away. Okay, yeah, go ahead. Yeah, we are neglecting quantum
Yes,
effects.
sir, but if we consider the electronic Fermi
Right, then we can't.
then we can.
No.
So, sir, in that case, what we can do?
So in case of molecular dynamics, similarly, we are thinking of a collection of atoms, for example, in their electronic ground state. A lot of times we can ignore quantum effects, but again, it's not always. If you go to close to 0 Kelvin temperature, like cryogenic systems, like at really low temperatures, or some special situations, then we cannot ignore quantum effects.
And sir, for properties which are predetermined by the quantum effects,
Right.
like the magnetic moments and all.
Mhm.
So in that case, we need to necessarily preserve the quantum effects.
Right. Then we have to perform the summation. We cannot convert it to an integral in that case.
Like the discrete summation. will
Right.
proceed.
Mhm. We have to sum up from one energy state to the other, and we have to we have to sum. I guess it's break time. That's why it probably went off. Oh, it's back on. So do you want to take a couple of minutes break? Sure. 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 Yes, thank you.
That's as warm as I could find.
Yeah, this was warm. Thanks.
It's funny because they had, they had cases of water sitting there on the,
Okay.
and so I said, can I buy water? And they said, no, those aren't for sale, those were for another office.
Okay.
So I asked Sujit and these guys standing there, I said, where can I get some water? And they said, just grab one there. I said, no, they told me. So they went in and talked to her and
It seemed like a shop,
twisting
right?
up.
It looks like a shop.
There's a shop, but the water is separate. It's
Oh,
for,
okay.
it's for some office. That's,
Oh. Yeah, I did see a
That's not
lot of
fixed.
water, but I didn't know it's. Uppercase N, right?
Uppercase n is a number of particles,
Hmm?
and the volume is V.
Right.
That is also fixed.
Okay, so let's continue. The slide is not showing up yet. Oh, it's showing up here. Okay. So we defined the system partition function, and we talked a little bit about the configurational potential. Like I mentioned, realistically, a lot of times we assume that basically the potential function, which is a function of the location of each atom in that collection, can be broken down to pairwise interactions and pairwise functions. So that's what we typically apply in most simulation systems like methods. So we can kind of assume that the only interaction that is happening is pairwise, meaning we basically sum up the configuration or potential energy of a certain atom interacting with the rest of the atoms in the system as a sum of the pair energies with respect to each atom in the system. So that's why Rij, where we are summing I from 1 to n minus 1, right, and j goes from greater than 1 to n. So basically, you're capturing all the pair interactions between the n atoms in the system. Okay, this is an approximation, but it typically is not a bad approximation to make. So what do we do once we have this pairwise potential? In theory, what we can do is describe the state of the system in terms of what is called the virial. Virial means slightly different things to, depending on the phase of the system you are interested in. In the gaseous phase, for example, it relates to the equation of state, which is basically a constitutive relation, right, for that particular, let's say, real gas. So the virial equation of state gives you PV over RT as a function of, obviously, if PV over RT is 1, then we are talking about ideal gases with no configurational energy. But in real gases, there will be many different virial coefficients, B, C, D, etc. So you can kind of expand on this. It's like a series of virial coefficients, which are each functions of temperature over specific volume, and then you have a specific volume square, cube, and so on. Okay, so the idea is, if you know the configuration potential or pairwise interaction potential, then you can actually derive the virial equation of state in terms of each of these virial coefficients from calculations. If you are interested in the mechanical properties of a crystalline system, for example, on the other hand, what you can compute from the virial is the atomistic level stresses, or the stress tensor actually, for each atom in that crystalline system or amorphous system, what you are interested in. So basically, if you have certain boundary conditions of pressure, volume, and number of particles in the system, you can, if you are able to specify this pairwise potential or interaction function, then from that you can model the system to calculate either its constitutive relation in terms of the virial equation of state, or the virial in terms of the stress tensor per unit atom that constitutes that particular system. Okay. So this is pretty powerful. So I'll just briefly talk about the most common potential here, which is Lennard-Jones, though tomorrow when I talk about molecular dynamics, I'll show you a wide range of interaction potentials depending on what sort of system you are looking at. The simplest one in theory is either the Morse potential or the Lennard-Jones potential, which basically has a dispersion term and it has a short range repulsion term. So if you have atoms that come very close, then you have a kind of a rigid wall almost. It's a soft sphere model, right? If it were a hard sphere model, it will be something like this will be a vertical wall here, but it's not vertical. Let me erase this. So this is an example of interaction potential, since we are talking about pairwise potentials in the previous model. So any questions? The Lennard-Jones potential, it's just a very common, it's called a 612 potential. It describes the interaction between atoms in a system in terms of a short range repulsion, which is captured by a r raised to, in terms of the r raised to sigma over 12, where sigma is the ionic, equilibrium distance between the two atoms in the system. So that captures the short range repulsion, and there is a 6th term, so sigma raised to 6th term, which captures the long range dispersion. I will visit this in details when I talk about about molecular dynamics tomorrow. This is just showing you an example of the pairwise potential. Okay, at this point we saw, we discussed basically the statistical mechanics foundation behind calculation of thermophysical properties of these systems. Any overall questions before I move on to showing some examples of how we calculate properties?
So that ensemble you discussed.
Mm-hmm.
In case of that quantum potential or the potential where the ensemble this and that, like this ensemble
Mm-hmm.
and the quantum potential or the quantum work, these are correlated or like it is different, entirely different from
If you're talking about the ensemble, that will be a very complex function, right? It will be a n-dimensional function, because that configurational energy phi will be a function of all the location of all particles in the system. So, we simplified it in terms of pairwise additive function. So, what I showed in the previous example in general is a pairwise function. It is a potential as a function of distance between two atoms I and j basically. But if you are talking about the ensemble, then in its full complexity, that will be n-dimensional function, very complicated.
all other directions will also contribute.
Not directions, it is all the location of each particle in the system. It is called gamma space. So, I talked about degrees of freedom earlier, right. So, basically to describe the collection of particles, you need 6 n coordinates, where n is the number of particles in the system. 6 because you need to know the location, which is in 3 dimension 3, and you need to know the momentum / velocity. So, if you know the location and momentum for each particle in a system, in an ensemble, and there are n particles in that ensemble, you have 6 n degrees of freedom for the ensemble itself, the entire collection of particles. It's called it's the phase space of that system. It's a gamma space. Right. Okay, if there are no questions, let's look at a quick example of calculation of properties. So, I introduced you to the lithium ion battery example yesterday, and like I mentioned, one of the key properties there for the electrolyte that we choose, we were looking at ionic liquids, and I mentioned what the merits are for those electrolytes. One of the key properties is the solubility of oxygen, because these batteries breathe in oxygen, and the oxygen has to be soluble in the electrolyte medium. If it's ionic liquid, we are talking about ionic liquid electrolytes. So, it's important to know the solubility of oxygen, because a higher solubility of oxygen would mean more effective oxidation of the lithium ion at the cathode, which will form some sort of a lithium oxide, right. So, we need to estimate the solubility of oxygen and connect it to a continuum scale model to be able to predict ultimately the specific capacity of that battery. Basically, the higher the solubility, the specific capacity of the battery should increase. However, these properties have not been measured in the specific ionic liquids we were looking at. So, I will give you an example of a calculation to calculate the solubility of oxygen in ionic liquids. This particular ionic liquid we were considering is called methyl propyl pyrrolidinium. I will quickly show you the structure. So, this is the anion, it is called TFSI, and this is the cation, which is called MPPY, methyl propyl pyrrolidinium. So, we have a liquid salt made of these two ions essentially, and we want to understand calculate what the solubility of oxygen is. So, the thermodynamic principle for calculating that property is through what is known as the Henry's constant. Okay. So, the Henry's constant, if you know the Henry's constant of a gas with respect to a liquid, then the solubility of that gas in that liquid is given by the partial pressure of that particular gas over the Henry's constant. The method for finding Henry's constant is pretty complicated. So, here is an expression for Henry's constant using a setup such as this. So, we have an ensemble, we were talking about ensembles. So, our ensemble or collection of atoms in this system is a set of ionic liquid molecules, which are shown here. So, on both sides of this, we have a semi-permeable membrane separating the ionic liquid with basically oxygen molecules. Okay. So, the semi-permeable membrane interacts with the oxygen in a way that it allows oxygen molecules to diffuse through that membrane to the ionic liquid, but it would not let the ionic liquids diffuse to the other side. So, that is why semi-permeable. So, to calculate the Henry's coefficient, we use a thermodynamic theory or expression which is given by this, and I have explained what each term in here is. This term, the P is pressure basically, and the suffixes 1 and 2 refer to the gas we are looking at, in this case oxygen, and 2 refers to the liquid, which in this case is ionic liquid. Okay. V2 infinity is partial molar volume of oxygen dissolved at infinite dilution, which means if you have oxygen dissolved, at infinite, just one oxygen molecule dissolved in this ionic liquid, that is infinite dilution. What is the partial molar volume? That is V2 infinity. There is the gas constant. Density of oxygen in the oxygen domain, which is on the other side of the semi-permeable membrane, and a coefficient known as the fugacity coefficient of oxygen. What is the fugacity coefficient? Fugacity coefficient phi is given through this expression that involves the condition the oxygen gas is in, including pressure, density, temperature, but also one of the virial coefficients. So, that is why I wanted to show you this example, because we talked about the second virial coefficient, and here you see that we have the second virial coefficient B, okay, appear here. So, basically if we can calculate each of these parameters from our simulation, we are able to plug that in to calculate the Henry's constant, and from the Henry's constant we can calculate the solubility of oxygen, which was the purpose. So, what interaction potential did we use? I talked about pairwise potentials, and I am just kind of showing you here the interaction potential and how complex it can be in these calculations. You see, this is the interaction potential, and you must be wondering, why are there so many terms? We just saw a simple looking Lennard-Jones potential. What are all these terms in this expression? So, the Lennard-Jones potential is still in here. This is the Lennard-Jones potential. Like I mentioned, there is a Rij raised to 12 and Rij raised to 6 term, the 12 and 6 term capturing the repulsion and the dispersion forces. There is a electrostatic interaction term, Qi, Qj are the charges on the atoms we are considering. But then what are some of these terms? So, what these are the energies of each of the bonds, angles or dihedrals in these molecules. So, the internal degrees of freedom are also important, right. So, we have to capture the bond energy, the energy due to the vibration of angles as well as dihedrals, right. So, this captures the pairwise potential for this system and the bonds in this system. So, we basically equilibrated these systems and let the oxygen atom diffuse through the semi-permeable membrane to calculate the parameters I just introduced in the previous slide. So, we were able to calculate all these parameters, including the mole fraction of oxygen that has diffused in the ionic liquid domain, which is very important, x1. Okay. So, from this you can plug it in to calculate the Henry's constant. Henry's constant's units are in atmospheres, or basically pressure units. So, the blue curve shows the Henry's constant, but before we look at the Henry's constant for this particular ionic oxygen in this particular ionic liquid, we have to validate our model. In this case, like I said, there weren't many experimental data available, but at 323 Kelvin there was some experimental measurement available for what is known as methyl butyl pyrrolidinium based ionic liquid, that is the cation, and the same anion as the one we are looking at, TFSI. So, it just means instead of the propyl in the side chain, instead of having 3 carbon atoms, it is a butyl chain. So, they have 4 carbon atoms. That should not really change the measured solubility by a significant amount. So, it should be about similar, and the experimental data had kind of a large error bar, but it was about 1210 plus minus 600 atmospheres, and our calculated value for the methyl propyl pyrrolidinium based ionic liquid was in the same range, about 990 atmospheres. So, that gives us some confidence that we are not completely off in this calculation, and what we are really interested in here is capturing the trend. What happens with temperature to the solubility of oxygen, right. So, the Henry's constant from our calculation drops with temperature, and what we and because the solubility is just inverse of the Henry's constant, is the partial pressure over Henry's constant, obviously the solubility of oxygen in the ionic liquid goes up in a nonlinear fashion for this particular ionic liquid. We did check for it is not guaranteed that the solubility of gases in liquids increase with temperature, it depends on the polarity of the solvent, etc. But for ionic liquids, we did check the literature for a different ionic liquid which showed the same trend. So, the trend is captured correctly and we have the solubility. The reason the solubility, if you wanted to understand why does the solubility go up with temperature, you have to look at this expression and each of these individual terms. One of the most important terms here is the mole fraction of oxygen that diffuses in, and from our calculation that increases with increase in temperature. Basically, at higher temperature it's easier to go beyond the energy barrier for solvation in the ionic liquid. So, therefore, the mole fraction increases, and that is a term in the denominator which reduces the Henry's constant, and therefore, we have this trend of Henry's constant for oxygen going down with temperature, and inversely the solubility goes up. So, this is an example of a calculation of a thermophysical property solubility from by applying principles of statistical mechanics through MD simulations. I will show you a very different example now, which is for amorphous structures, solid structures, in this case sodium sulfide, silicon sulfide glasses. Okay. I introduced this as well a little bit yesterday in terms of application. I talked about using these amorphous structures as solid state electrolytes for solid state sodium ion batteries. One of the challenging aspects is to map the ionic conductivity of these structures as a function of the composition. Simply put, these are amorphous structures, much more complicated than pure simple crystalline structures. So, there is a lot of variability, and even in experimental measurements. So, we are interested in identifying the transport mechanism of sodium ions in these electrolytes and connect that and determine the structure of these electrolytes and connect the activation energy for ion hops in these electrolytes, and therefore, the ionic conductivity to the structure as a function of the composition of these glasses. Okay. So, I will skip the methodology details because I have not yet introduced ab initio MD. But what is very important in theoretical methods, and we always have to validate our calculations with respect to experimental measurements. In this case, we had some X-ray scattering data for these amorphous structures, namely 50% sodium sulfide and a mixture of 50% silicon sulfide glasses. Okay. So, the key structure in these glasses are these SiS4 tetrahedral structures. You see the green atom is the silicon atom, and each of these yellow atoms are sulfurs. So, you have an SiS4 structure which forms a chain in some shape or manner. It could be an edge shared or a cornered shared type of a connectivity, or under certain compositions it could be just almost isolated tetrahedral units. Okay. It depends on how much sodium sulfide you have added relative to the silicon sulfide. So, we calculated density from our calculations and compared it to, so our calculated value was about 2.02 grams per cc compared to the experimental measurement, which showed 1.98. So, that is pretty reasonable comparison. It compares pretty well with the experimental data. And we also compared the location of the peaks. You can see this G of r is what is known as a pair distribution function across various distances. So, in this case, this G of r is obtained from the X-ray scattering for all atoms, all pairs of atoms in the system. You could have a resolution of certain pairs or include all pairs of atoms in the system. In this case, it is all pairs. So, there are distinct peaks for silicon sulfur at about 2.1 angstrom, which is basically the distance between silicon and sulfur in this tetrahedral unit. So, it matches pretty well the location of that peak with the X-ray scattering data. There is another peak for the sodium sulfur pairwise interactions, and then there is a third peak, the triangle here, for sulfur sulfur. So, with this initial understanding, we took that data and converted it to structure factor space. Okay. You have structure factor versus this Q distribution from the X-ray scattering and our calculations from ab initio molecular dynamics. What you see is on this right side, beyond about, it is in 1 over angstrom units, beyond about 8, there is pretty reasonable agreement between our calculations and the X-ray scattering data, and this is a short range order of the glass. So, the ab initio MD captures the short range order pretty well, but the long range order, there is some deviations between the calculations we have and the experimental data. It is kind of expected, also because the ab initio molecular dynamics method, which I haven't yet introduced, are pretty expensive computationally, and we are limited to only about 100 to 200 atoms. In this case, I believe we did 144 atoms. So, it is pretty limited in terms of sampling. So, and the long range interactions it can model. So, not surprisingly, at larger length scale we are not comparing very well, but it does capture the short range order of these glasses pretty well. So, we wanted to understand how these tetrahedral structures that are connected, either edge shared or corner shared, this network, and the interaction of the sodium ions with the sulfur in particular impacts the ion hop mechanism of a sodium ion from one side to the other. We also wanted to understand how what the corresponding activation energy or energy barrier is for sodium ion hop, and are there distinct mechanism or only one mechanism for that ion hop. These were the questions we wanted to answer. So, first we tried to understand if we have a sodium ion. So, this is showing the silicon and sulfur ions. Let's say the red ones here actually are sodium ions. So, we add a sodium ion to this system, the cation. On an average, what is the coordination of this sodium ion with sulfur and nearby tetrahedral units? To determine that, we calculated something which is from the pair distribution function, which is the coordination number. So, we found that the sodium ion on an average is coordinated fourfold with both sulfur and silicon, meaning SiS4 tetrahedral units. So, on an average at a stable state, each of these sodium ions are surrounded by 4 sulfur ions, or coordinated with 4 sulfur ions and 4 different tetrahedral units as they hop. But there can be some metastable states where they are either under coordinated or over coordinated, which would lead to what we have is the energy landscape for these ion hops. So, what you see here in this plot is an energy landscape which shows as the ion, as a sodium ion, let us say it starts out here, moves across with respect to its neighboring ions, sulfur and silicon sulfide tetrahedral units, what the energy levels are at each of the different configurations. So, I have a nice schematic here to demonstrate that. It is actually a short movie showing you, at each configuration what is the coordination structure of a sodium ion, shown in red, with respect to the green atoms, which are again the green spheres are silicon sulfide tetrahedral units, the center of mass of that, and the yellow spheres are the sulfur. So, like I mentioned, it starts out with a stable structure with 4 neighboring sulfur atoms and 4 neighboring silicon sulfide tetrahedral unit. But as it goes through these saddle points and transition states, the number of coordinations with the sulfur and silicon sulfide tetrahedral units varies. For example, when you are at state C, you have 3 and 3. As you let it go beyond that, as you are going, you see it changes all the way to the minimum energy minimum structure E, when it comes back to 4 and 4 stable coordination structure. So, it starts from a stable structure and ends up with a energetically more favorable structure during this discrete ion hop. And we use this climbing image nudge elastic band calculation to track that and calculate the energy as the sodium ion hops through this amorphous structure. So, what can we gather? So, this is type 1 hop. So, we analyzed our system and identified 3 different hopping mechanisms, this being the first one, we call it type 1 hopping mechanism, and the total energy barrier for this is given as 0.31 electron volts. Type 2 hop is shown on this slide. So, in here we start from this energetically favorable point A, we go through a first transition state which has a lower energy barrier, we reach a saddle point and we go to a next transition state D, which has a pretty high energy barrier EB, and finally, we end up with a energy minima structure at E configuration. So, again starting out with 4 and 4, going to 5 and 4, then as it goes to D, you have a 3 and 4. So, it is under coordinated with the sulfur, and finally, it lands up at this stable site E, which is coordinated 4 and 4 with both sulfur and silicon sulfide tetrahedral units. Okay. So, in this case, the activation energy is a lot greater than the type 1 hop. It is 0.67 electron volts. So, obviously, these hops are seen a lot more frequently in our calculations than type 2 because of much higher energy barrier. Okay. And then we have a third one. Again, we looked at the energy landscape for that. This is somewhat simpler in the sense there is only one transition point, but the energy barrier for this is also quite high. So, this animation shows you again how it goes from, I can play that once more, 4 and 4 to 4 and 3, and then finally again back to 4 and 4 in this case. And the energy barrier is 0.62 electron volts. Okay. So, this is good. We have identified 3 different hopping mechanisms, but how do we kind of connect it to other physical properties and ionic conductivity ultimately for this system, right? So, what we did for that is we drew from a very well established theoretical model, which is known as the Anderson-Stewart model. The Anderson-Stewart model basically connects the energy barrier for ion hops in an amorphous system with the distance from the initial location for that hop, the initial location of the cation, to the final location of the cation, which is known as the hop distance. So, let us look at the expression from Anderson-Stewart's model. So, the Anderson-Stewart's model determines the total energy for the ion hop, the energy barrier that is, which has 2 components. The first one is the electrostatic energy barrier or activation energy, and then the other one is the strain binding energy. Okay. So, the first term is given here as a function of a few different parameters in this system. The partial charges on the cation and the anion, in this case we are talking about sodium and sulfur, the dielectric permittivity of vacuum and glass, which is a fixed value for a certain composition of the glass, and it is also a function of the radius of the anion and the diffusing cation. Okay. So, the anion the cation is coordinating with, and the radius of the cation itself. There is a displacement factor beta, which is also a function of the radius of anion and cation, but also of a parameter called lambda anion, which is the distance between the 2 anions across which the sodium ion is hopping. So, this is a 3-dimensional hop through a doorway. So, and the distance of the 2 coordinating the cation coordinates with the sulfur atoms, right, and ions, and it hops between them. So, the distance of the 2 sulfur atoms through which it is squeezing through, if you want to think about it, is given by this parameter lambda anion. On the other hand, the strain binding energy term, so this was the electrostatic, this is a strain, is a function of the it's a function of the shear modulus, it's a function of a parameter called the doorway radius, which I will show you in a moment, and lambda cation, which is basically capturing the hop distance. Okay. So, what we did for some reason this does not show up, give me a moment. Okay. So, what we did is we used the Anderson-Stewart model in conjunction with our calculated total energy barrier. Directly from the simulations, we are able to calculate each of the terms in the electrostatic binding energy, the electrostatic contribution to this barrier, because we have all these parameters available from our calculations directly. We can plug it in and we can estimate delta EB. We have the total energy barrier already from our nudged elastic band calculation. So, we can subtract it and we can calculate the strain binding term, the energy barrier for the strain binding energy term, right. If the shear modulus of this amorphous structure, the glass, is known, which it is in our case, we can basically infer the doorway radius from this Mackel-Frisch-Howitt model. The doorway radius is R d. So, we can calculate for R d because we know everything else, we know the hop distance. So, given these hop distances in type 1, type 2 and type 3 transport of the sodium ion, and the total energy barrier from the climbing image nudged elastic bands, we calculated the doorway radius for these 3 distinct hopping mechanisms as 0.477, 0.271 and 0.282. I believe this is nanometer. Okay. So, 4.7 angstrom, 2.7 angstrom and 2.8 angstrom. So, does this make sense? Now, let us take a look at the energy barrier for each of these hops, which was summarized here. So, type 1 had the lowest activation energy or energy barrier, and what we find is the doorway radius for that ion hop is the biggest or largest, it is 4.7 angstrom. So, basically the sodium ion has a larger space to hop through for that particular hopping mechanism type 1, which explains that the energy barrier is the lowest of all the 3 hopping mechanisms. Okay. So, questions?
Sir, is the doorway radius related to the saddle point area or something?
So, let us see, I had this schematic. So, here is the doorway radius. So, you have this structure here through which the ion is hopping. So, you can take the silicon sulfide tetrahedral structure and you know it is the radius through which it is a 3-dimensional structure, and it is the radius available, the space available for the sodium ion to go through. We are not directly calculating it, we are estimating it from everything else that is known using the Anderson-Stewart and the Mackel-Frisch-Howitt model.
Sir, is it anywhere related to saddle point?
Yeah, I mean, your question is what is the location of this doorway, whether it is at the, you know, if I look at the energy landscape, where exactly this doorway radius, it is at one of the transition states, B or D, yeah. So, the larger volume you have for the ion to diffuse, basically that opens up, that increases the doorway radius and reduces the energy barrier for the ion hop. So, this is all good. The ab initio MD simulations gives us insights into the mechanism of sodium ion diffusion in these amorphous structures, which is fairly complex. But again, we are limited to a system size of only 150 atoms, which is pretty small if, to let us sample and calculate properties such as diffusion coefficients of these ions and ultimately the ionic conductivity. So, to get around that, we applied the next, I presented to you yesterday the various models or methodologies across length scales, and the next one up, if you remember, was classical molecular dynamics. So, one option was to use classical molecular dynamics to look at much larger systems, let us say hundreds of thousands of atoms, to sample and calculate, post-process and calculate properties such as ionic conductivity. The challenge was, for this particular glassy amorphous material, sodium sulfide, silicon sulfide, there weren't any standard parameterized potential for this specific glass that we could use from the literature to start modeling. The general function for, or general form of potential for these materials, sulfide glasses, is met by the Buckingham type interatomic potential, but the exact parameters for it. So, here is the mathematical form of this potential. There are a couple of constants involved, as you can see, A and C and rho. So, these are certain parameters that need to be used as inputs in this model, but these were not available for this specific type of glass. However, it was available for the lithium sulfide silicon sulfide counterpart, you know. So, what we did was we started off with parameters for lithium sulfide, silicon sulfide, and then we ran DFT and ab initio calculations to determine these coefficients A, C and rho is the ion specific length parameter. This process is called parameterization of a pair potential, which is what you have to do if it is not already available. So, in the molecular dynamics method, what we did is we followed a technique that is actually used for making these glasses, which is the melt quench. So, you heat up the constituents atoms or in the glassy system to a very high temperature and then rapidly quench it. Obviously, the quenching rates in MD are much higher than in the actual physical process for making the glasses, but at the end you have a glassy structure after you run through this melt and quench system process. So, mhm. So the ionic conductivity is a fundamental property. We are not modeling at a certain voltage. We are just looking at the ion diffusion in these systems fundamentally, and that is related to the ionic conductivity. So this is the melt quench method, as you can see. We heat it up to 3000 Kelvin and then quench it to 300 Kelvin and maintain it for several picoseconds to equilibrate the system at 300 Kelvin, and then after it's reached an energetically favorable structure, the energy is fixed or constant, then we can sample to post-process and calculate any physical property we are interested in. And you can see in this case we are able to model a system much bigger because our domain size is 8 nanometers by 8 nanometers by 8 nanometers. So we are certainly modeling tens of thousands of atoms here. So again, yeah. Yeah, it is very high. Right. Of course, there will be there could be some metastable phases formed because you are using such a high quench rate. So that's why it's important to kind of try out different rates and holding temperatures. In this case, 3000. We tried a few. I'm not showing here. And then finally, when you have the quench structure, to validate it with respect to the experimental data. That's the only way out to kind of make sure that the structure you have is reasonable. Oh, in MD simulations, you remember we are only limited to, 100 nanoseconds, let's say, right? So if you want to heat the system up to, let's say, 3000 degrees, and you are only, the computational resources only allow you to model systems for tens of nanoseconds. You have to have high quench rates. Same deal with mechanical property. Those that are looking at strain rates with molecular dynamics simulations typically have very high strain rates that you're looking at. It's pretty much impossible to look at realistic strain rates given the time scale available for molecular dynamics simulations. So our calculated density did not agree as well as the ab initio molecular dynamics. Remember, this is a fitted pairwise potential. So there is, it's an empirical potential that we fitted to capture the interaction. This is not completely accurate, as we'll find out later. So there's a little difference between the density, which is 1.93 from our MD simulations, and the experimentally measured density. But it's not super significant. It's less than 5%. So we compared the structure from X-ray scattering, the ab initio molecular dynamics, and classical molecular dynamics. I'll show you the structure factor versus the Q space data. So what we find is when we look at classical molecular dynamics, we get a much better long range order or medium range order agreement versus the short range order shows quite a bit difference from the X-ray scattering data. This is the opposite of what we found from the ab initio molecular dynamics. Remember, there we had a much better agreement for the short range order, but a bit of a difference for the long range or medium range order. So again, that's because even if you parameterize the potential quite accurately, a simplified function such as the Buckingham potential, like this, is unable to capture all the complex angular interaction or third order or fourth order interactions in this. We are just looking at a simplified pair interaction. So there are obviously some errors involved in that.
So these X-ray scattering, these are done experimentally?
Yes, this was done at Argonne National Lab, and we availed that data, and there is a software to convert the raw data from there to either the structure factor or pair distribution functions. And then, from the molecular dynamics simulations, you calculate the same pair distribution function or structure factor. If there is interest, I can show you during my tutorial how you do that conversion. I have a code that I can kind of present here. So that way you can directly compare the calculations with the experimental data. This is my own code. Well, the Argonne National Lab has its own calculation software for finding that. I mean, that's something that they provided to me. But my software converts my pair distribution functions to structure factor. That is mine. Okay. Right. Right, it's the structure factor. It's the structure factor. It is related to the pair. I will present the mathematical expression for it when I kind of go over that tutorial. So, what we did, what we can do with this molecular dynamics simulations, because our sampling is much better, we have a much larger length scale that we can access. We can use this expression, which is basically a fluctuation dissipation theorem based expression, to directly calculate the ionic conductivity as a function of displacement correlations. Okay. So, this expression, just briefly, Zi and Zj are the partial charges of the diffusing of this various atoms in the system. This is basically the displacement of the atom with respect to an initial location, and this is a displacement of another atom in the system. So, it captures both correlated and uncorrelated motion. It is a little different from diffusion coefficient based on mean square displacement, where you are only looking at uncorrelated motion for self diffusion coefficient. Here you capture both correlated and uncorrelated motion of the ions. So, this is an expression we use for estimating the ionic conductivity of this system, which is plotted here with and compared with ionic conductivity measurements. So, the red circles are measurements and the black squares are calculations. You can see we overestimate the ionic conductivity pretty much for at the range of temperature we looked at, but we are still capturing the trend pretty well. So, also if you fit a Arrhenius expression to this, what you can calculate from this is the Arrhenius activation energy for these ion hops, and they agree pretty well between our classical energy, MD simulations 0.44 electron volts and the experiments 0.43 electron volts. Okay. Now, why are we over predicting the ionic conductivity? We did some analysis for that. Given our pair potential, what we found is from experiments, there is quite a bit of edge shared tetrahedral structures in this amorphous structures, but our calculations were primarily corner shared. So, that opens up quite a bit of non-bridging sulfur atoms. So, non-bridging sulfur atoms, basically you have some more sulfur atoms that are not connected to the neighboring tetrahedral unit, and these non-bridging sulfur atom sites lends itself pretty well to sodium ion hops, and therefore, our calculated ionic conductivity is greater than the actual measured ones, because we did not quite capture the edge shared structure as well. We also leveraged the enhanced sampling that is afforded by molecular dynamic simulations to look at varied compositions by changing the composition of the mole fraction of sodium sulfide relative to silicon sulfide in these systems. We looked at 33%, 67%, 50-50 and 67-33. Okay. And this agrees with the experimental trend that as you keep increasing the sodium sulfide concentration in these glass compositions, it basically opens up, frees up these silicon sulfide tetrahedral units, and therefore, there is a drop in the density. This is observed from experiments, and also our simulations captured the drop in density with increasing sodium sulfide content. So, we try to understand what happens to the structure of these systems as we increase the sodium sulfide concentration of sodium sulfide. So, we captured that through various pair distribution functions, the sodium-sodium pair distribution function, sulfur-sulfur and silicon. This one is remarkable because what we find is as the concentration of sodium sulfide is increased to 67% here, a second peak kind of emerges for the sodium-sodium peak, which kind of suggests that there is a new site for sodium hop that is opening up besides the closest nearest neighbor site, which is captured by the first peak, there is an additional site for sodium ion to hop to that is opening up. So, our hypothesis at that point was this should enhance the ionic conductivity of these at these compositions as we go from 33% to 67%. So, to verify that, we calculated the ionic conductivity of these amorphous structures at these distinct compositions, and indeed we saw quite a bit of enhancement in the ionic conductivity, about an order of magnitude as we went from the 33% sodium sulfide to the 67% sodium sulfide, which is attributed primarily again to this additional site that is opening up because of the extra non-bridging sulfur atoms as the sodium sulfide content in the glasses increases. Now, at this point we did not have any experimental data, but luckily we were able to have these glasses made and characterized, and that captured this a similar trend from the experiments as well, which was pretty satisfying that we captured at least the right trend in the ionic conductivity with these compositions, and it is pretty important to be able to increase the ionic conductivity for solid state electrolytes. So, I will stop with that and see if there are any questions on this topic.
So in case of the X-ray scattering experiment, if there are any X-ray absorption in that case, like we talk about the exams, extended X-ray absorption spectroscopy.
Right.
So in that case, like you talked about the structure factor that thing. So that can also be computed from.
XAPs can be used and compared with unfortunately not classical molecular dynamics, but with ab initio molecular dynamics you can extract from the simulations. I have seen publications that have done that. I have not compared data directly with XAPs, but my understanding is yes, you can do that. For example, it is done for molten salts and other amorphous structure. For molten salt reactors like nuclear salts, fuel salts, there is a couple, there are reports of XAPs being computed from ab initio molecular dynamics as well and compared. I think there is Oak Ridge National Lab has a software perhaps to do that, as far as I know. So yeah, it's possible, but not with classical molecular dynamics. Remember, with classical molecular dynamics, we don't have the resolution at the electronic scale. We are just looking at the atomistic scale.
Sir, one more question regarding the density of state.
Mm-hmm.
You sir initially discussed that the Fermi dynamic distribution of
Mm-hmm.
state, and then you talked about some equal probability of occupying those quantum states.
Mm-hmm.
So density of state is kind of linked with that probability thing, or
Right, density of states is the occupied states in an electronic material. Yeah, so I didn't quite get your question.
I wanted to know that like in that Fermi dynamic distribution,
Mm-hmm.
we talked about the number of atoms and
Mhm.
the number of electrons in that particular quantum state. So from there we can derive the
Yes.
density of states.
Mm-hmm. You can run calculations, typically density functional theory calculations, to obtain the density of states directly by solving the quantum level. At the quantum level you can look at the energy states occupied by the electron, and from which you will get the density of states. It is also possible to analytically calculate it, but not very straightforward for very simple systems. But I think typically computational approaches such as density functional theory is used.
So can you explain this parameterized force fields once again?
What?
Force fields you have mentioned here.
The potential model used for this study?
The next slide. Next one. Yes.
Oh, the parameterization of the force field. So parameterization of force field has to be done by, basically what you're doing is you have these parameters A, B, and A, C, and these coefficients that you have to fit to be able to get the function that gives you the right property. The question is, what is your benchmark property that you're comparing with? In this particular case, we compared with the density of the glass. So we use parameters to get good agreements as far as the density of the glass goes, and the coordination number between the silicon and sulfur, right. So, you have to, the parametrization process is basically determining parameters to agree with certain measured properties. In this case, these were the ones that we compared against, but it does not have to be. Force fields are parameterized in different ways. For example, this other OPLS force field that I showed you for the previous calculations, which we did not parameterize, it is a standard force field. This one was parameterized based on solvation energies. So, each force field can be parameterized with respect to different properties. That is why, even for simple systems such as water, a lot of times there is not a force field that captures all properties, including the density of water, the dielectric constant of water molecule, or dipole moment. There is several potential models for water. There is tip 3P, tip 4P, SPC.
Basically dependent on the
what property you are trying to capture most accurately. For some systems, you are able to have a pair potential that captures a wide range of properties. In other cases, there are only a few properties that you can parameterize against. Other questions? Thank you for your attention.